Yeah. Hello everyone. I am Ajinkya and I will be your host for this today's webinar for next 40 to 50 minutes, and we will be interacting. As we all know, today's webinar topic is the FPGAs using Zybo Z7 board. So here is the quick agenda of our today's session. We will go through the theory sessions at first, in which I will brief you through the introduction to the FPGAs, latest Xilinx FPGA families. Then I will discuss each and every block of the Zinc architecture in detail, and then we will go the overview of towards the overview of the Zybo Z720 board, and we will discuss some clocking and power options and the other peripherals as well. It is expected to take 20 to 25 minutes for this theory session. Then we will proceed on the live demo, in which I will show you the live board present over here in our laboratory, and we will be implementing a 32-bit counter, and we will be able to see its and debug its output. Yeah. I will also, in this session, I will also guide you how to use the Vivado tool in order to implement that project and how to make it happen. Let's After that we will be going towards the higher end project, which will be live communication, UART communication with my Zybo from my Zybo board to my PC. We will see how a Zybo board is sending a message to the PC, and we are able to decode it, and we can see that message. So which these two live sessions will be followed by the closing note of our director, and then we will have a Q&A session for the participants who have, if you have any doubt, I request you to keep them in a written or any format so that you can ask it at the end. Also, in order to get the maximum experience of this live demonstration, I will request you to pin the account name Live Zybo Z7 on your screen, so that when I am demonstrating the board, you will be able to see the board and my screen simultaneously. What are FPGAs? Let's begin with that. FPGAs are basically pronounced as the field programmable gate arrays, which are nothing but the matrix of the CLBs, wired interconnect, switch matrices, and I/O banks. These configurable logic blocks are nothing but some RAM and a flip-flop and multiplexers, through which we can implement any digital logic whichever we require, and we can configure them to act as a whatever choice we require. Let's say I want to use the NAND in my digital logic, so I will configure my mux accordingly in order to use it as a NAND. And these interconnects, wired interconnects, are used to connect both of more than one configurable logics to each other. And obviously, switch matrix acts as a router for the wired interconnects. Next, we have I/O banks through which we can communicate with the external world. So this is all the basics of the FPGA. This is almost present in every FPGA, and that's how the FPGAs were built up. Now, why to go for the FPGA? If I have, let's say, if I decide to manufacture a circuit and I want to establish certain operations, and so for that I have two options. I can go with the application specific ICs or the field programmable gate arrays. The application specific ICs, once designed and manufactured, their functionality cannot be retained, cannot be changed. Whereas the FPGA, on the FPGA board, if we want, we can erase the existing program, and we can do we can configure it with a with a new programming, new application, and the updated versions as well. Next, we have the advantage of the development boards that are available and that are ready to take, whereas it becomes, if we are going to manufacture any circuit or let's say any product at a small scale, we do have onboard peripherals as well, so that we can use them and we can configure them. So they are readily available. They reduces my market to time. That's the advantage of the FPGAs. Next, we will have a quick overview over the Xilinx FPGAs families available over in the market, which are the RTX, Kintex, and Vertex. Typically, there are the typically the semiconductor devices speed of is based on the space between the PMOS and the NMOS that they are implemented. The lower the space, the higher the operating speed and higher the configurations that we can achieve in the in the per unit area. So this RTX family typically operates at the 24 nanometer and more range, whereas the Kintex and the Zinc families are working at the 20 nanometer technologies, and Vertex provide the high performance speeds and everything like in the 16 ongoing with a 16 nanometer technology. Since we at the SION Semiconductor are working with a different projects and different onboard chips, we have chosen Zinc to be as a decent one where we can go with all the required speeds and we can test and debug and perform our laboratory R&Ds. I will guide you one by one through the Zinc 7000 family architecture. As we have seen, it has many I/O ports and multiple options available with us to process with. Beginning with the application processor unit, this consists of the two dual-core Cortex A9 processor, which can be function in order to achieve the complex programming. Before that, I will like to tell you this whole architecture is divided into the two systems, which is the processor system and the configure custom logic. The basic part that we have seen CLBs, VIOs, they are mostly lying in the custom logic so that we can customize them and add them accordingly. This processor units hardware is pick and fix, and we can processor systems hardware is fixed, and we can configure them through the various registers and the options. So my application processor unit consists of two dual-core CPU, which are powered by the ARM, which works on the reduced instruction set machine and can be operated as on the 32-bit bus basis. In order to support this ARM Cortex processors, we have two memory management units, which helps to read and fetch and write the data from the physical memory that is existing on the board. And these MMUs works in order to translate the virtual data address, that is the physical address, to the virtual address, which can be processed by the processor and further back. To support this data transfer and the access of the easy access and fast processing of the data, we have two caches, one for the instruction and one for the data cache, which can have which are the 32 KB of the memories and are managed by the Snoop controller unit. The Snoop controller unit basically takes care. Suppose I am using both of my CPUs, both of my dual cores together. Let's say I want to synchronize a data that is that is processed by one processor, and it has to be updated to the second processor. In that case, this Snoop controller will take care about that synchronization and will transfer this data from one to another. Along with that, we have advanced watchdog timers and timers which can be used as a counter, and that watchdog timers are used in order to reset the system if something goes wrong. In order to support the primary data caches, we have 512 kilobits of the level 2 cache, and along with a controller, which in accordance with the Snoop controller, gives the data to the CPUs and stores the recently used instructions. Next, we have 8 DMA channels, which are used to establish a communication between the APUs and our on-chip peripherals through AXI slave bus. Next, we have on-chip memory, where we can store our program in order to run it. And we have this can be acting as a secondary memory, secondary memory along with the flash that is present on the board. And let's say I have a certain application. Once the interrupt is triggered, that needs to be completed in the timely manner. So in order to give the fast access to the APU cores, we can have this, we can store that part of the application in this on-chip memory, which will be assessed by the Snoop controller, and the results can be achieved within the blink of eye. Next, we have system clear registers, watchdog timers, and timers, system control registers, watchdog timers, and timers, which similar to the watchdog timer or acts and keeps tracks of the running processes and can be used to reset the whole system. And the control registers are used to configure the particular IP or the onboard peripheral in order to make it work. Let's say I have Ethernet, which can be operating on the 10 Mbps, 100 Mbps, and the 1000 Mbps speed. If I want to use 100 Mbps, I can configure it to operate on the 100 Mbps speed. Next, intercommunication between our custom logic and onboard peripherals is taken care by the generic gigabit interrupt controller. This controller does processes all the interrupts that are arriving from the DMA channels, application units, and the onboard processor, and provide them to the CPU. And the CPU, in accordance with a priority set, will process those interrupts and act upon them. DDR2 and 3 controller together acts as a memory interface and use the functionality to achieve faster data read and write. Let's say if my CPU is supposed to read the 100 bytes of data from my memory memory interfaces. In that case, my CPU will issue a command to the DMA controller that we have to read the data. And CPU will be free from its operations. CPU will not be engaged in this reading operations. So through the memory interfaces, DMA channel will read the data, and DMA controller will read the data and provide the interrupt to the CPU once data is done. This interrupt will be taken as a signal as a feedback from the DMA, and CPU will get to know that we have got the data and we can ready to process it. In a way, I can save the CPU time, and which can be utilized to serve the other peripherals or the application. The I/O interfaces available with us consist of high speed and low speed bandwidth peripherals as well. High speed and low speed peripheral controllers, which include USB, Ethernet, UART, and CAN. Let's say I want to use this Zybo board in an IoT environment. So in that case, I will configure this with my Ethernet controller. And once I receive the specific board package, a specific packet that is intended for me, and I am placed on the LAN, I can be able to decode that packet on the hardware basis and store it into the RAM. And then we can use that data in order to process it or display it or simply store it in a SD card. So simply by configuring these available boards, we can achieve the multiple embedded applications. Next, we have a central interconnect which acts as a controller and let's say interface between all the available peripherals, and we can, as per our requirement, either through the APU or through the custom logic, we can use and we can access any data or anything that is available on the board through the interconnect system. Next, we have custom logic. In the programmable logic part of our architecture, we have custom logics where we can put on our particular data. Let's say I want to implement any digital logic which has a four RAMs, which has four flip flops and combinational circuits. Where I will put this logic, I will program this through either through any one of the hardware description language. I will put them on the custom logic, and if required them to communicate with use any peripheral, I will go with them. Next, we have EMIOs. So this communication with the peripheral, like I said, it is used through this extended multiplex IOs. Along with this EMIO, we can, if we want to communicate this peripheral data to the external world, we have the 54 pins of MIO which can be configured dynamically to communicate with any one of the peripherals. The four general purpose boards are used to connect to the interconnect, and which can be communicating through the data, which can be communicating through the custom logic. Next, we have high performance boards as well, which are used to which can be used to configure the high speed peripheral devices. The accelerator coherency port available in the at the interface of the PL and the PS system is directly connected with the Snoop controller. In a case where my Snoop controller is expecting some of the important data to be placed in the cache from the programmable logic, in that case, it will go with this accelerator. It will access that data through this ACP. Next, we have IRQs. Which are acting as an interrupt request, which will provide the interrupts, as I discussed already, to the gigabit interrupt controller, and we can get the access of the CPU through them. Next, we have configurable IOs, which can be used to communicate with the external world in order to achieve any sensor or any data that is coming from the external world, and we can fetch that and use them in our system. Now that we have done with the discussion of the architecture, I would like you to show we are left with the reset and the clock generator part. The whole programming subsystems comes up with a reset, which is connected to the hardware manual reset button as well, which can be used to pre-configure or the reset level power on, which can bring the board back to the power on configurations. Whereas the clock generators here are the most important unit, which can be used to generate a various clock of up to 667 megahertz, which can be provided to the different peripherals according to their specifications. We will discuss in detail in the clocking section. Now that we have understand the Zinc 7000 architecture, let's go in the brief of our board We have here various Ethernet controllers, USB, Ethernet. Like I said, we have various on-board peripheral controllers available, DMA and a high performance ASL slave ports, and the dual core Cortex A9 processor makes it the most suitable choice for our requirement. Since we have various units, various teams that are working on the different projects, which includes Ethernet, live video transmission, NVMe, PCIe stack, we can availability of all these available peripherals makes it the best choice for us to go with the Zybo Z720 board. Now I will quickly guide you through the each and every peripheral that is available with me on the board. First, we have a power switch, which can be used to turn on and off the power. Then we have power select jumper. As we will discuss in the power section, we have three available options, and we can set this jumper to the different positions in order to use it. Then you have USB JTAG / UART port, which can be used in order to communicate with my PC, and also we can extract the power from the USB. We have user LEDs. When the MIO ports are being used, these LEDs will glow up. We have multiplex IOs, programmable devices ports, which can be used to connect outer the devices with my board. I will request all the participants to please stay muted and stop your videos. The USB 2.0 host and the 4TG port can be used along with this board in order to give some data to the transfer some data to the, let's say, my USB device. If we are not going with this option that my board, we do not want our board to act as the USB host, then we can disable this USB port so that we can be stringent on our power budget and we can save some power. Then we have standard pre-mod ports, which are operating at a regular, which are operated along with our external devices. Then we have user switches, 4 user LEDs on which we will be demonstrating one output. We have MIO user buttons as well, which can be used which are the push buttons which can be used along with the MIO ports. High-speed PMOD ports are used for the high-speed applications and the device connections. Then we have 4 push buttons, RGB LEDs. Then we have analog to digital converter port, has a dedicated ADC port as well, which can be used with the analog sensor data. We have audio codec ports as well, which can be used along with a speaker or the microphone in order to work with audio and stereo mode of operation. Then the white strap over here is embedded with a 48 bits of the MAC address that this board possesses. This MAC address can be used when the board is placed in the network and we wish to access that board. Along with that, we have external JTAG port as well, which can be used if required. But since on this level, we are going with a USB programming. We have a USB controller which is interface along with a JTAG port as well. My USB data can be converted to the JTAG format, and it is my FPGAs can be programmed through them. But additionally, they have given us the option to connect our JTAG connector as well. Next, we have HDMI receiver port. If suppose I want to transmit any video or the audio data, like we know HDMI is typically related with the video data. We can receive that data, which can be buffered into our processing system, and we can process that data as well. Next, over here, we have a PCAM connector, which can be used to connect a PCAM module, which comes up externally, and we can connect video data as well. Then the SD micro slot available here can support up to 512 MB of the SD card, which can be used in order to store the data or the program. If my on-chip memory is not enough in order for the processing. Next, we have HDMI TX port, through which we can transfer the data that we wish to require and which can be seen on any monitor on any HDMI compatible port. Next, we have Ethernet port, which can be used along with the 10 Mbps, 100 Mbps, and 1000 Mbps speed. Along with that, we have external power supply connector, which can be connected to the 5-volt wall adapter. And let's say my application is taking too much of the power consuming too much of the power, which in turn result in the high dissipation of heat. And heat sink alone is not able to control the temperature. Then we can connect this board with a fan, which should be operating on the 5-volt and 3-wire. Can be connected through this 3-wire port. Next, we have this programming mode select jumper, which are used in order to decide which program it has to run, whether it has to run from the flash, whether it has to program online, but where it has to program through the JTAG, or it has to load the boot image that is stored. Next, we have power supply LED, which indicates the healthiness of the power plant. Once if we are programming a board, we can see this LED as a feedback that our programming is completed and on the board. And we also have a processor reset button, where we can which is connected to the reset or block from the PS module, and we can hard reset the processor. Next, we have FPGA clear configuration button as well, which can erase my dump program from the board, and we can be ready to dump the new program. Next, over here you can see the heatsink profile underlying which is the heart of this board, which is the Xilinx 7000 FPGA. Then we have DDR3 memory controller as well in order to support this FPGA. As I said, we have 3 available options for the power supply. We can take either through the wall adapter, which should be 5 ampere, and my board can sync up to the maximum of the 4 ampere of current, which can be taken from the power supply or the battery. And most commonly, if we are not going with a high-end applications and the peripherals, we can go USB supplied power will be enough. Just that the USB supplies 5-volt and 0.5 ampere, giving me 2.5 watts of the maximum power, which is well below my 0.75 limit. USB 0.5 ampere is well below my 0.75 limit of the board. Then we have in the clocking section, we have one onboard oscillator which generates the 33.33 megahertz clock, and which can be used along with the PLLs in order to achieve maximum of 600 megahertz of frequency, 667 megahertz of frequency. And this custom PLLs can generate 4 reference clocks in order to be used. Along with that, we can use multi-mode clock managers and 2 dedicated PLLs in order to generate 4 more clocks, which can be used and which can which gives me opportunity to form a wide net clock tree. And next we have another option for the clock we have, that is the Realtek Ethernet PHY, which can supply me the 125 megahertz of clock available, which is taken at the input of the PL process, PL block, and we can use them along with this dedicated PLLs and the MMCs. As I said, we have three available options for the programming mode. Let's say I have 16 MB of the code flash. If my program can lie in that flash, I can load it with the program, and upon boot up, I can load it as the first thing to start up with. And this flash, let's say, since we are using since we want to be printed one welcome message on the HDMI port on the monitor that is connected through HDMI port. So I can configure the board, I can write a program, I can generate its image, and I can load that image in this flash memory, so that whenever my board is power on, it will display that same message. It says SION Varsity on my monitor that is connected together. If that 16 MB memory is not enough, like I said, we can take the help of the external SD card, and which can be used once these two modes are typically used when the processor is deployed on the application. Whereas in the laboratory purpose, when we are testing and debugging various developed applications, we will go with a JTAG mode of programming, where we can reprogram and use this. Depending on the jumper position, the processor will decide which program to be given the priority in order to execute. Then we will quickly discuss few of the I/O peripherals that are available with us. Like I said, we have micro USB peripheral, which is controlled by the FT2232 USB to UART bridge, which acts as a controller for the JTAG and the USB programming as well. This USB controller is onboard USB peripheral, typically communicates with 115200 baud rate and 8-bit character length. We also have, apart from that, Ethernet, USB, HDMI, and the audio codec filters. Ethernet can operate up to the 100 Mbps of the speed, which is achieved through the Realtek 8211E5, and USB is supported by the microchips USB 3320 chip trans receiver chip, which can allows me to operate up to 480 Mbps of the speed. Next, we have two HDMI ports, like I discussed, which our transmitter port is unbuffered, which directly provides data to the transmitter port, and the receiver port is a buffered one, which has it has the memory, so that received data will be stored in the port at first and then accessed by the processor. These are the type A wireless HDMI ports have the type A receptacles. The audio codec and ports and allow me to generate my microphone and the speaker along with my processor, which can be operated from the 8 kilohertz to 96 kilohertz of the frequency. Apart from that, we have few push buttons, switches, and the tricolor LEDs. Like I said, we have fan. We can connect fan. We can connect PCAM port in order to achieve the live video transmission. We have the PMOD ports as well, which are the grouped together in the 12-pin formats, as we have seen on the board. Out of which one is a high-speed analog digital, one is a high-speed port, one is dedicated analog digital port, and three high-speed ports, three high-speed ports, one dedicated analog digital port, one standard port, and one MIO port. These connectors are typically grouped together in the form of 12 female connectors, which out of which two dedicated pins, 6 and 12, are will be supplying the VCC of 3.3 volt available on the port, which can be used by the external circuit, and also provides with a ground on the pin number 5th and 11th. Now it is almost time that we have reached, and we will be proceeding with a demo counter demo, and I will first guide you through how to implement this demo in the form of Vivado project, and I will show you how it is supposed to function. So yeah, we will be implementing the counter using the IPs using the IPs that are available with us. Xilinx and or AMD provides. Whenever it comes up with a board, it has a wide range of the IPs which we can use through, and we can configure them as per our requirement. So here we will use a counter IP which is connected to the clock enabled port, and which will be used through the VIO, and the output will be displayed with help of the ILA as well as the LEDs. We will pass this 32-bit data through the slicer, and we will take the four MSB bits on and display them on the LED, so that you can visually see the data changing from 0 to 15, which is 0000 to 111. The clocking wizard here connects with us 125 megahertz system clock available on the board, and we will be down converting into 100 megahertz clock. My VIO, ILA, and counter will be operating on the 100 megahertz clock, so that my 32 bits will be incrementing at the speed of the 100 megahertz with respect to the speed of the 100 megahertz clock. In order to make it visible by the naked eye, we have just used the four MSBs so that we can see the differentiate that the counter is going up. And yeah, for those who are new to this FPGA world, I will like to just give some brief on the VIO and ILA. Let's say I have a analog amplifier, and I want to test it and debug it. So here my binary counter is analogous to the analog amplifier that I am supposed to test, whereas the VIO are the function generator, which will pass some inputs. Here our input will be control enable, and we can along with function generator, we use the CRO in our lab to observe the output waveform and monitor the waveform. So my ILA is analogous to the CRO, and which connects my board output pins to my Xilinx software, and we can see visually the counting sequence that is going up from. So similar to our laboratory testing, we do have this functionality that we can observe the output. So my ILA and VIO together gives me more observability and controllability over the circuit. I will quickly guide you on what are the steps that are supposed to be done, and next I will show you once our project is ready, which is ready, what I have done in this project. I will guide you through this slides, and we will implement that project on our board, and we will see that. Once you open the Vivado, which is a suite available at the AMD site, and you can download it, you can register, and once you open, you will get this tab where you have to click on the create project, so that you will see something pop up like this. You just can define the location where project is being stored and the name of the project. Then we will start with a RTL project because we will be going on with either with a block level or the RTL project. And these projects can be used, other options can be used if someone else has done the synthesis part and we want to move further. So we will go with RTL project system. Next, we have constraint files of we have two options to define the constraints. In order to know the Vivado tool that we are using these IO pins, we will define them in this constraint file, and whatever my inputs and outputs are there in my logic, they will be mapped to the IO present on the board, and we can achieve the synchronization. Next, we have to select the Zybo Z720 board available over here. XC7Z020CLG401 is the name of the FPGA that is lying over there on the board, so that the Vivado tool gets to know that we are dealing with this kind of FPGA, and so that it will give me all the available IP options along with that FPGA, and it will preset load the default board settings. Next, once we click on the confirm, we will open this. This kind of screen will be open in your Vivado design tool, which the flow navigator to the left side automatically guides me through the all the design flow, where I can add some sources. In the language templates, I can see various resources that are available with my Verilog and VHDL languages, and I can get an information on the syntax and how to use them. We can use the IP catalog in order to add the IP. This is the one way where we can. There are two ways in which we can implement a circuit. We can go either by writing the Verilog or VHDL, basically a hardware description language project, or we can go directly by the block integrated way, which I will discuss you, which we will be using in this demo. Next, we have once our design is ready and we can run the simulation if we want. We can test them through by passing on some simulations. We can write some simulation files, test bench, which are typically called as the test benches, and check our IOs. And in the RTL analysis phase, there the tool checks whether the program is written as per the coding guidelines or not. Let's say I am using a register and I am using two blocks at a time, and I am assessing a value to them from the two always at passage block when I am programming with a Verilog. This will create a timing conflict, and which is not desired and which is not standard way of writing. The simulator tool will simulate it. There is no issue with the simulation, but when it comes to the hardware, it might create a timing race, and that's why it is not a standard industry practice. So the RTL analysis part will give you such errors or warnings or the critical warnings based on the severity of the mistake, and we can recommend it so that we can reduce the production time and we can solve these bugs at the early stage. As I said, we have RTL analysis, then we can go with a synthesis option where our program also block level design is converted into the schematic. Then we have run implementation option where we can see the design being mapped on the available ports and the custom logics and everything on the board. And then once we enter the pin constraints as well, and we are good to go with a bit stream generation. So in order to create a block level design, we need to click on this create block design and give you the name of the design, and we can add this. We will get such a kind of screens over here. If we click on the plus add IP button, we can search on the counter IP that we wish to install, and we can place it over here, and we can configure it to the 32-bit or let's say 8-bit, whichever we want. And we can add other peripherals as well, ILA, VIO slicer, and a clocking wizard, and we can interconnect them. Once we validate the design, it will say we should get this message that the validation is successful. If there are any errors, we need to rectify them. Next, we will be getting. Next, we have to write. The pin constraints. Like for this project, we will be using this clock signal, which is available at my K17 125 megahertz clock. As I have named, since I have named it as a system clock in my block, I have given here the get ports this clock, which will connect my package pin K17 with my input of the clock in my design. And this create clock is optional, which is used for the timing analysis. We can add them as a clock name, and we can give the time period of the clock, which is 8 nanosecond typically, and waveform 0 indicates that the first rising edge will be at the 0 second, and the second and the falling edge will be at the 4 second. In this way, we can custom the duty cycle of the clock as well. Then we are mapping our output LED ports that we have defined in our in our block to the actual LEDs present on board, which are which are connected to the pin ports M14, 15, M14, 15, G14, and D18. Next, once we launch the runs, that is, we have to select once we set up the SDCC as is design constraint file, we can go on with a synthesis, then implementation. Once synthesis is completed, we have to go with the implementation, then generate a bit stream, and once we open the hardware manager, I will show you the further process in the live. So by the time I request you all to see the live Zybo Z7 board as well, which is pinned on my screen, and so that you will be able to get the maximum out benefits. So I will give you 2 minutes. If you cannot see the board, you can change the option in the view, and side you have to select a side by gallery, so that you will be simultaneously be able to see my screen and the Zybo board as well. I hope you are able to see my screen and the board together, so that we will proceed with the further demo. Once, let me just reconfigure this board. So that I have turned off the board, it shows that the hardware is disconnected. Once you open the hardware manager, you will get a tab something like this, where we can program the board. Okay, so if you power on the board and you keep the programming mode to the UART, and you will be able to observe programming devices here, available name of the device, which is Digilent. Once I select the program device, it will pop up me towards the bit string location which we generated in the previous step till now. And once we program this bit string, and the programming mode is done, LED glows on the board, which indicates my program has been done successfully. Now, as you can see on my screen, there are two tabs that are open: hardware ILA and hardware VIO. We connected our 32-bit output to our ILA, and here we have also connected that output with our VIO, which will show me the 32-bit value, and we have connected one output of the VIO to the input of my counter, which will be acting as an enable circuit, which is set, as you can see, which is set to 0 now. If I click overheat, it turns on to 1, and my counter starts counting, as we can see. The last 4 bits are connected on the board over here. So this 1, 2, 3, the MSB value is displayed over here. As of now, 0, 1, 0, 1, which means 5 is going on, which is incremented to 6 now, and which we can see over here on the LEDs. If you are able to see it, I will show you the closer views. 1011, 1100, and like way it is going on. If I stop this counter from my VIO, it will not be proceeding further. It is stuck with the 1111 value, which is shown over here as F. Now I will rerun this again, and I will capture this data using the ILA. So my ILA captures certain 2048 values of data, certain of the amount of data on this and shows it on my screen. As we can see, it was 0 at the time when I captured. So it was incremented from the 91, 92, 93. So in this way, my up counting process is going on. I will request you all to please please keep your videos off so that our participants can see the live Zybo on board. So as we have demonstrated here, we can see the counter being implemented on the board. For the next demonstration, I have a UART program. I have a UART program with me. Give me a second to configure it and open the tab for you all. Yeah, basically this is the overall. So basically, this is the overall architecture that we will be implementing along with in order to demonstrate a UART project. We will use the Xilinx Vivado tool to configure my board with a Xilinx processing system, which we have discussed in our architecture, and I will export that hardware file to the to my VT tool, which is provided by the Xilinx itself, along with so that I can configure the high-end applications using the C and all methods. And we will be implementing one message on the board, which will be sent to the which will be sent to the PC, and which will be decoded by the PC's USB host using one Teratom software. Now Teratom is nothing but a one snooping tool which will get the access of that communication port connected with my PC, and whatever the data that my board will send to the PC, it will be accessed by the Teratom software and will be shown on the board. So here, basically, we will be configuring this processor system, and we will be making one file ready along with a USB port enabled, USB and UART port enabled, so that we can pass on the data. We will dump one program into this memory interface module, and which will be processed by this APU, and which will be then converted into the provided at the UART port using my multiplex IOs. So once we are ready, so this is the block diagram. This is how we enable the processing systems. Once we go to the block level design, we add IP, we add link processing system. We generate a bit stream overheat. We can run the block automation, which directly configures that system to the defaults, and then we have to generate the bit stream, and then we have to export this hardware along with a bit stream like this. We can follow these procedures. And next we have to go to the tools, and then we have to open the VTs. In the VTs, if we create on the application project, we have to use that hardware file, which is extended with a .xsa extension, and this file has to be open in the VTs tool, so that the VTs tool will then we can generate a application overheat, and we can choose wide range of default applications as well. Otherwise, we can go with our custom application, which we can write in the C program. And from here onwards, I will like to go in the VTs tool in order to give you the live demo. So like this, we have created an application. Now we will be running this. Once my application is ready to run, it will be here. It will run over here and will give me this message. This message is from Zybo Z7. Welcome to SION Varsity. In order to prove that this is a live demo, I will add on Saturday, 16th December. So I will quickly save this message. I will revalidate. I will build this application so that these changes that we made are reflected in the new file. And along with that, I will have to configure my Term software, which I will show you once we open. If you download a Term, which is for typically build up smoothing software for the Windows, you will see this kind of pop-up once you open the software. Since we are going to have the USB port, we want USB ports data. We will configure it with a USB COM5 port. And okay, and like I said, my board will be communicating at the baud rate of 115200. So we will set that baud rate and the new setting, so that whenever my board sends any message, it will be available over this terminal and we can see it. So from you just keep and watch over here. I will run the software from the VTs tool. I will share you how to run that also, so that yeah, once you are ready with your application build is finished, you can run as and launch on the hardware. Since there is some other program actively running on the hardware, which is our counter program, it uses pop-up that one session is running and we do want to relaunch. Yeah, we will say yes, relaunch. Now, as we can see, our LEDs have gone off, blinking, and we can see the programming done module LED has glowed. So we need to see the terminal on the UART as well. We will show them. Yeah. See, once I run the program, this message arrived over here on this terminal. This is the message from Zybo Z7 on the Saturday, 16th December. Welcome to SION Varsity, which concludes our. I will rerun it again so that you can, with sharing this UART screen, so that you can see it live. See, we got another line saying this is message from Zybo Z7. So there. That brings us to the closure of this session, which was the live demo. I will request you all to further proceed. We will be proceeding by our closing note by our director. So hand over to Mary for the further proceedings. I thank you all for listening me patiently, and we will after this closing note, we will take a Q&A.
Yeah. Hi, this is Basha. I'm the director of SION Varsity. So thank you for giving opportunity, Mr. Ajinkya, for giving a good presentation, and it's a good explanation about the Zinc board. And come to now about discussion about the SION Varsity. So SION Varsity is the venture for the SION Semiconductor is for the mainly for training and development purpose we started here. At the same time, it's mainly providing for certification courses and all, and for globally we are planning for this. Our global headquarters is there in Chandos and USA. At the same time, our branches is there from Bangalore and Hyderabad also. At the same time, our operations is going on from Singapore and Malaysia. And mainly we are providing here for fresh student pursuing candidates and pass out candidates also. We are providing internship programs. Okay. Internship and student enhancement programs we are providing. As you know, many of the colleges and universities also, they are expecting the internships for the students to enroll for the 6 weeks to 6 months of internship they're expecting. So for that reason, SION Varsity is planning to provide the internship for them in VLSI and embedded domain. At the same time, to enhance their knowledge from the in academic knowledge to industry standard knowledge. For that reason, we are providing student enhancement program for pass out candidates. So in that, for internship, we are providing FPGA ZN, SOC verification, and embedded system. For student enhancement program wise, we have different types of courses. We are providing PG diploma courses and certification courses and protocol based courses. The main thing we are providing this thing, we have to make a bridge between the academic to the industry. For students, they have to more helpful for entering to the education to the industry and how to process and how what are the ways we have under to enhance to give the chance to them to enter into the industry. For that reason, we are providing. Okay. At the same time, we are providing unique opportunity. They have training for industry standard training and 24 by lab assistance and placement assistance also we are providing. And we are doing the placement assistance and we have in our own companies, they have providing a placement assistance. At the same time, we have several clients also is there. For them also, they are contacting us for the requirement, any requirement is there. We are providing that kind of assistance for them. It's a good chance to enter into the SION. So we hopes you also understand about it. If your students or anybody interested for internships and getting the courses, we can recommend. And we have upcoming webinars also we are approaching you. They have different webinars we are going to conducting in future. There is a opportunity for semiconductor industry. At the same time, AI camera design using Xilinx FPGA and ultra high speed Ethernet system design we are providing. At the same time, VR video conference system design also for professors. Target of participant also mainly for professors. We are providing this webinars in the year of 2024 January and February at the time. So further, any queries we have, we can ask. Now we'll start the questioning and answering session also. Mr. Ajinkya and Mr. Anil is there and taking care about this questioning answering session related to Zybo boards. We can able to discuss. If yeah, now we are allowing to participant to unmute your mic. Okay, if we have any queries, we can discuss. Feel free to communicate with us. Yeah. This is Ajinkya over here. I will request you all to feel free to communicate with us regarding any technical or non-technical queries, and you can ask us us for the assistance or the internship or anything. You can. We at the SION are always ready to interact with the educational background people, and I would also request you all to fill the feedback form and the certificate of participation form in order to get the certificate of participation. If we don't have any query, we will wait for the few minutes
and then we will declare the end of this session.
So at the same time, we already shared the link in the chat box. We have to fill the form and submit for certification as per your certification name and all we want to mention it. Please fill the form and submit. We'll get the certification to you. As per that name, what you fill in the form. At the same time, if you have any queries, you want to discuss anything on Zybo board, please feel free, you can ask the question.
Okay, then we will end up the session. I request you all to copy the form links posted in the chat box, and so that you can get the participation certificate. And thank you for joining. Thank you for listening patiently. Thank you from the SION Varsity. Okay. In order for you to copy this certificate link, we will keep this session live meeting ongoing for the 5 minutes, so that you can copy and do the registration for the meeting. So here the technical team is signing off. Thank you all.